Guys, today we'll be discussing lead code problem 191, which is number of 1 bits. So basically, this problem wants us to take a binary representation of a number and return the number of 1 bits that are present in it. So if we have this example, right, so we can see that this representation has 3 1s in it, or 3 1 bits in it. Therefore, the output is 3. So there are two ways of doing this problem. The first one is pretty obvious, which is you traverse through the entire integer, so which is 32 bits, because every integer has 32 bits in it, and check manually if each bit represents 1 or 0. And if it represents 1, you can just take a counter and add 1 to it and return the counter. But that's also like in terms of time complexity, that works out because that's constant time. You run the any loop you run, while loop or for loop, that will go for 32 times in the worst case. So you still have O of 32, which is constant time. But I want to show you a solution today which is kind of unique in terms of the approach. But this also has constant time, but in terms of like the approach, it is quite unique. So if I have a number, let's say 1011, right? Basically what I do, this algorithm, which I think also is a very unique one, you just have to from this number you have to subtract 1 first. So you have this, right? And whatever result you'll obtain after subtracting 1, in this case, I'll just do it quickly. So you get 1010 after subtracting 1, and when you take the AND complement between these two numbers, you would get 1 0 1 and 0. Right? That's the AND complement between the two numbers. Now, if you compare these two numbers, right, you can see that there's 1 at the end becomes a 0. So this one iteration of this expression would lead us to be have a result of 0 at the end. So we count 1 bit eventually, because our condition is until the number is not equal to 0, right? So we count this 1 bit over here and we repeat this process. So we subtract 1 from this now, which would give us this would be 1001, I guess. And if we take the AND complement between these two, we get 1 0 0 and 0. Okay, now in this case we kind of get rid of one more 1, which becomes 0. So our second iteration would give us a second one bit, which is present in the number. Now we have this number, right? So we take this number, we subtract 1 from it, which would lead us to if we subtract this number from 1 and we take the complement, we'll get rid of this 1, because the AND would result in these two becoming 0. So that's what our final iteration would be in this case. So that's what we do. So if I can implement this, if I take a counter, right? So if I have count equals 0, which would basically count all my 1 bits, which is present in the number. And I will run a loop, let's say a while loop. So I'll run a loop while n is a positive number. And while that's true, I will perform this expression this algorithm which I just mentioned, which is n will be n and n minus 1, single AND operator. So you have n equals n minus 1. Right? And while that's done, we count plus equal 1. And when that's done, we return the value basically. So that's what we do in the entire expression operation. And when we run this, we kind of get the result to work. Our cases are passing and runtime is 35 milliseconds. So if we submit this, then we probably will get a result which kind of works. And yep, it's accepted. And it's a pretty efficient solution because it runs under 14 MB of memory. And obviously it's in terms of time also, it's pretty good. So this was my what I learned from this problem, and I hope you were able to learn something today. So thank you for watching. Bye bye.